Welcome to episode 5 of the London Futurist podcast with your co-hosts David Wood and me, Calum Chace. We're attempting something rather ambitious in episodes 5 and 6. We try to explain how today's cutting-edge artificial intelligence systems work, using language familiar to lay people like me, rather than people with maths or computer science degrees like David. Understanding how transformers and generative adversarial networks, or GANs, work means getting to grips with concepts like matrix transformations, vectors, and landscapes with 500 dimensions. This is challenging stuff, but do persevere. These AI systems are already having a profound impact, and that impact will only grow. Even at the level of pure self-interest, it's often said that in the short term, AIs won't take all the jobs, but people who understand AI will take the best jobs. We're extremely fortunate to have as our guide for these episodes a brilliant AI researcher at DeepMind, Aleksa Gordić. So, buckle up, and here we go.
In this episode, Calum and I are joined by Aleksa Gordić, who can be described as a double rising star. First, he's a rising star as a creator of AI systems, taking advantage of the latest developments in deep learning. But second, he's also a rising star as a communicator about developments in AI. His personal YouTube channel, The AI Epiphany, features over 100 educational videos and is approaching 1 million views. Today, Aleksa, I ask you to bear in mind that listeners to this podcast aren't especially knowledgeable about linear algebra. They probably can't tell the difference between a convolutional neural network and a recurrent neural network, and some of them might not be able to tell the difference between a matrix and a matrix. But these listeners are all interested to understand better what's going on in AI just now. They don't want to hear an unreliable, misleading, exaggerated account, of which there are many on the internet. They do want to hear from someone with a grounded, deep understanding of what's actually happening now and what might happen in the next year or so. Who better to answer questions on that subject than you, Aleksa? So why don't you start with a brief introduction about yourself?
Thanks a lot, David. Thanks, Calum, for having me here. That was a great introduction. So, briefly about me, I'm currently a research engineer in DeepMind. I broadly work on projects related to multimodal learning, which means basically combining multiple modalities such as visual information or textual information and trying to make some sense out of that multidimensional stream of data. So that would be, my current role. Before that, I was at Microsoft working on this HoloLens device. That's basically a holographic device developed by Microsoft. And the idea is to put it on your head, and then you're interacting with 3D holograms in the world around you using your hands, using your eye gaze, etc., etc. And I guess final thing I would like to note is that I never had a single formal course in machine learning. I'm completely self-educated. My official background is in electronics and in hardware, so I kind of had to teach myself all of this in my free time, basically. And some of those things I picked up during the work at Microsoft as well. And finally, everything I say in this podcast is pretty much my personal opinion. Just want to put that out there. I'm not representing DeepMind here.
That's really impressive and suggests that there's hope for all of us yet then. So, as David said, we want to really try and get an explanation of what transformers and the current state-of-the-art AIs are, how they work, in a way that can be understandable to someone like me, a layperson who's not a mathematician, not a computer scientist. So in the last two episodes, episode 3 and 4 of this podcast, David and I went through the Big Bang, which the general narrative is happened in AI in 2012, when machine learning became applicable to AI. Machine learning wasn't invented then. The term machine learning was coined in 1959 by Arthur Samuel. It's a branch of statistics that's been around for a while, but in 2012 it became useful in AI. Jeff Hinton and other researchers using an algorithm called backpropagation got it to work. And since then, AI has done something which it had never done before, which is it's made a lot of money. And that's really the acid test of how useful a technology is. And machine learning is different from the previous kind of learning in that it is a system in which machines create models, populate the models with data, and use those models to arrive at decisions or conclusions which they're not explicitly programmed to do. It's not magic, it is statistics, but they are learning as they pursue a goal, and that's a pretty decent definition of intelligence. So if that's an acceptable description of what happened in the Big Bang in 2012, something else happened in 2017, which is the arrival of transformers, and that's really, I think, where we pick up the story today.
Yeah, if I can say a couple of things about 2012, that was a big moment, and it's usually referred to as AlexNet moment because the neural network that entered the competition called AlexNet basically has beaten the competition by a big margin. There was not a novel approach by any stretch of imagination. So CNNs have been invented by, I think, I might be wrong here, Fukushima or something. I might be wrong here, but in the 90s popularized by Al Nakun and others. And they were already working, but the main ingredient here was that we had data, we had big data, we had much bigger neural networks, and we had much better hardware, GPUs, to support that moment. People usually refer to that more as deep learning rather than machine learning. And the difference is, I guess, a subtle one, but usually when you say deep, you mean it has multiple layers or multiple modules or whatnot, some type of like deep processing, and that's why it's kind of a branding rather than accurate mathematical description of what's going on. But yeah, just a minor detail.
Is it true to say that deep learning is a subset of machine learning?
Deep learning is a subset of machine learning. Yeah, that can be definitely said, because all deep learning algorithms learn from data, whereas not all machine learning algorithms are deep necessarily. They can also be shallower.
And I've often heard it said that deep learning is really a rebranding of artificial neural networks.
Yeah, that's probably accurate to say, although deep learning is a bit broader term than just neural networks. It can really refer to anything that has, as I said, this recursive, iterative processing. So it's kind of vague, but usually people, when they say deep learning, they do mean neural networks, different types, recurrent neural networks, graph neural networks, convolutional neural networks, transformers, et cetera, et cetera.
So what's happened in 2017 and thereon with transformers? How does that change the possibilities of AI?
There was a beautiful moment. So in 2017, what happened is that a group of researchers from Google basically published this paper called Attention is All You Need that introduced the so-called transformer neural network. And it does not have, just to kind of put this out there, it doesn't have anything to do with Transformers, the movie, or like robots or whatnot. It basically means it's the original application that Transformer was doing in that paper was machine translation, or translating from one human language into another. Don't quote me on this, but I think it's either the fact that it's transforming from one language to another, or it's the way how it's transforming the data as the data is flowing through the model. So it's one of those things. Since then, it turned out it's much better than LSTMs.
LSTMs being long short-term memory?
Exactly. Introduced in, I think, 96 by Sebastian Hochreiter. I might have missed his name. And
Jürgen Schmidhuber.
Yeah, that's correct. So before that, LSTMs were kind of dominating. And then what happened is that Transformer has multiple advantages. So one of those advantages is that it can process data in parallel. Whereas with LSTMs, you kind of had to process data in a sequential manner. And the second very important difference is that transformers are much better at modeling these long-term dependencies. And what I mean by long-term dependencies is if you have a current word in the sentence, you really, in a human language, is such that you are oftentimes referring something that happened maybe a couple of sentences or couple of paragraphs, or even depending on the complexity of the story, it can happen even in the beginning of the book if you're reading a book. So you do want to be able to model these long-range dependencies, and transformers are simply much better suited to do that task as well.
So if I were to ask you, tell me more about that, you'll have to figure out what that refers to. And I want to ask you, how can transformers do that better than long short-term memory? Because I understand that was also an idea to preserve the context over a period of time.
Exactly. That will be an example of what I mean by a long-term dependency.
But why is the transformer better at doing these long-term dependencies than what was previously available?
Mm-hmm. Okay, so that's where the concept of attention comes into picture. And I don't know what's the best way to explain this, but I can start like this. So first, maybe it's useful to understand how transformer works on a very high level. I'm going to be very hand-wavy in explaining this, but like hopefully intuitive. So you grab a piece of text and you tokenize it. And what I mean by tokenization is you split it into smaller units. That does not necessarily have to be a word. It can be a subword. It can be something that we as humans don't consider necessarily semantically meaningful, but it's a piece of text. You then map those subwords into these higher dimensional vectors. And maybe a small digression. When I say higher dimensionality, people might be scared instantaneously. So basically, a simple explanation would be this. So we live in a 3D space. I mean, 4D, depending how you define it. But let's just focus on the geometrical aspect of the space. So you can basically specify a point in the 3D space by specifying 3 numbers, right? So you can say, hey, this is the X coordinate, this is the Y coordinate, this is the Z coordinate, and we know exactly where that point is in the space.
So it's like how far east, how far north, and how far you are above the ground.
Yeah, there will be a different coordinate system, but pretty much the same logic. And so what would be a multi-dimensional space is a space where you need, for example, 500 or 1,000 numbers to specify a point in that space. So nobody really has an intuition of what it looks like to be in the higher dimensional spaces. Even people like Geoffrey Hinton and Joshua Bengio. I think that Hinton famously said, when you say 500 dimensional space, just say it out loud and think in your head, like just imagine a 3D space, just like imagine a 3D structure. So like obviously we cannot imagine in our minds multi-dimensional spaces, but we can rely on our reasoning and logic and mathematical fundamentals to just infer that the behavior is going to be similar to lower dimensional spaces such as the one where we live in.
Okay, so that's a relief. We don't have to have some kind of model in our head of what on earth a 500-dimensional space is.
Nope, and nobody does.
It's just pure maths, and we just think about it in 3 dimensions. That's good enough. That's a help.
Exactly.
But what are these dimensions? If we have a word like princess, one dimension is that it's a female word rather than a male word. One dimension is it's a daughter word rather than a mother word. Another dimension is that it's a royal word rather than a common word. Is that the kind of dimensions you have in mind, or is there something more subtle?
So that's hopeful thinking. Optimally, that will be the case. Like it will be interpretable by humans, but more often than not, it's not interpretable by humans. You just end up with something that's useful to the model, and the inputs and outputs are interpretable to you as a human. But everything inside of the model is kind of black box. So that's the so-called black box approach, where you don't understand what's going on, why you're getting that result, but you do know how you trained the model, you know what you gave to the model as the input, and you understand what's going on at the output.
So to drill down on that a moment, so David's come up with 3 or 4 dimensions of the word princess. The other 496 are things which mean nothing to a human, but enable a machine to identify relationships between the word princess and the word slipper or the word pumpkin. And just wouldn't mean anything to humans, but it means something to the machine.
Exactly. And now there is just like, I need to mention this, there is a whole field of people trying to figure out what's going on. And there was literally a couple of days ago, came an interesting paper from Anthropic AI on the interpretability and people trying to analyze what's going on and what type of features are these neural networks learning. So one interesting example that was, I think, word to whack happened in 2013, if I'm not wrong. And back then, what they figured out is that if you take some word, like maybe you take a word woman and a word queen, and then you take a word man and the word king, and there's some nice properties that kind of emerge in those hidden so-called latent spaces of those models. And so what happens is if you take the vector, so that multidimensional point that represents the man and the king and the woman and the queen, and if you subtract man from the king, and if you subtract woman from the queen, you get basically, let's say, parallel vectors in that space. And so what you can do, like as a consequence of that property, is that you can subtract the woman from the queen and add that vector onto the man, and you end up with a king. So the model will predict you do that complex arithmetic, not complex, it's fairly simple actually, just to do that subtraction and addition in that space, and then out comes the king. Or you can do whatever combination, and that's just a single example. So those spaces tend to have structure. It's not like completely gibberish. We sometimes know how to understand what's going on there, but not everything is interpretable and not everything is explainable.
And what's interesting, I understand, is that the software looks at lots of text and figures out this mappings by itself. we humans don't tell it, hey, this is the feminine of this is the plural of that. These words typically go together.
Exactly.
It's able to work out by itself a huge probabilistic set of mappings. And so that if it then sees a sequence of words, it's able to say, well, here are some possible ways in which the sentence could be completed, or here are some possible ways in which the sentence could have been previewed and what might happen beforehand.
Exactly. And that's one of the nice things that transformers they did not invent the so-called self-supervised learning, but they definitely promoted that type of learning. So what I mean by self-supervised, so first maybe it's useful to contrast it with like supervised learning. So supervised learning is where, let's say you have an image and some human being somewhere basically labeled that image and put the label, for example, cat or dog or whatever. And then we used to train, so for example, AlexNet that we were previously referring to, how it was trained is basically you give that neural network, that convolutional neural network that are very nicely suitable for images, you give it the image, you give it the label, and you pass the image through the network predicts something, and then you penalize it if that something, that prediction was off from your target label. You just rinse and repeat. You do that, and then you train, and the network learns useful representations internally such that once you give it some picture that it has never seen, it can then predict the correct label. You always have a probabilistic output, and then it's not 100% certain that it's a single label. It has a prior over the output class labels.
Excellent. That's really helpful. Can I just go back to this word vector, because that pops up a lot and it confuses me. I suspect it probably confuses a lot of people. Is a vector a relationship between two data items or attention points, or is it one data point?
So vector is a point in this abstract vector space. So we'd get into some seriously abstract mathematics, but when I say vector, is probably the most useful is to think of it as an arrow in the 3D space.
Okay.
That's a very grave simplification of what a vector is, because vector is a super abstract and powerful concept, which can be a lot of things. But when I say vector, continuing on, the best thing I want you to have in mind is just consider it like an arrow in the 3D space or a point, because equivalently a point can be considered as a vector if you treat the origin as the default point, and then you can form the vector between those points. As I said, maybe the arrow would be the simplest mental model you can have of the vector.
And would it tend to join two things, like, for instance, queen and female?
Well, yeah, that would be an example of a vector. And if those 2 points are in 3D space, you can imagine the vector being the arrow pointing from one to the other.
So what's the output of this system? Why have people been impressed by what it's able to do?
We'll be right back after a quick break.
The People in Performance podcast offers insights into the strategic competencies, behaviors, and results needed to increase the performance of employees and leaders. The show looks at all areas of the world of work, including attraction and recruitment, onboarding, training, and succession planning. Tune in to get a better handle on the stages of workforce planning you need to master in order to guarantee long-term success in a rapidly changing world of work. New episodes drop each week. Check out the latest People in Performance episodes on your podcast platform of choice. Follow us on socials and read the latest articles at pppod.com.
Mm-hmm. So maybe just getting back to the self-supervised learning first, maybe just quickly to address that point. So self-supervised now, you don't have the labels, and that's so powerful because now we can leverage the vast amount of data, of textual information that we have on the internet and use it for free. We get the labels for free. So how do we do that? So what these transformer models, how they're trained is you literally input a sentence, a piece of text, a paragraph, textual information, and then you shift by one that same text to the right. And what you do by that, you're basically predicting the next token, the next word or subword or whatnot, as I previously explained. And by doing that, just predicting the next word, which you know what it is because you have the next words, right? And then for the final word, you can just predict some special token. And that's it. So you get the labels for free just by predicting the next token.
And the system sort of trains itself. It's not trying to always guess exactly the right word because there will be many sentences which are similar and have different words in them, but it has to come up with a probability distribution. So that if we said that the princess tried on the slipper would be acceptable, sock might be acceptable, crown might be acceptable, but tried on the golf ball wouldn't be acceptable.
Exactly. And so during the training, what the model does is we actually try and predict exactly the word that's the next word in the sentence. But if you keep on repeating that over many, many sentences, many, many books, many, many websites, you just end up with that type of statistical learning where the model can model the probability distribution across the vocabulary. It will probably put a higher probability on, what was the word you used in your example?
Slipper?
Slipper, for example, would be the most probable word. And then, for example, dog would be like super improbable, maybe 0 point and then 6 zeros and 1. That would be a possible output of a neural network.
So these models end up being absolutely vast, presumably.
When you say vast, you mean like big number of parameters?
Yeah, huge number of parameters.
Yeah, that's one of the trends. So the original transformer, I might be wrong here, but I think BERT was around 100 something, 300 million parameters. I would have to dig into the paper and see the actual numbers. And then since then, we had, I guess, orders of magnitude of increase in these models. So we had big models a couple of years ago were considered if they had like maybe 1.5 parameters and then 10 billion, like models such as Google T5 and Megatron. And then later we had GPT-3, which is probably something that some of your audience might be familiar with, which it was 175 billion parameter large language model coming from OpenAI.
We ought to explain what a parameter is.
Yeah. We have these artificial neurons, which are loosely inspired by biological neurons. These artificial neurons take the input, they multiply the input with some weight, and then we sum up the input and we pass it through some activation function. And so that you can think of that similarly to how a neuron works. So neuron has these dendrites, and basically dendrites are receiving some electrical signals, and then those signals are kind of accumulated in the body of the neuron. And then after a certain threshold, that neuron might fire and send the information to the next neuron. And we are kind of loosely modeling that. And so what a weight is, what a parameter is, those are, by the way, synonyms, are basically those weights of those artificial dendrites, the connections of the neural network. So that's what I mean by a parameter.
Which in the case of a biological neuron is a synapse, isn't it? The point where one dendrite meets the axon of another neuron.
That's correct. The synapses, yeah.
And different neurons are influenced in different proportions by other ones. So sometimes there's a connection between two neurons, but it has a low weight, when other ones are much more tightly bound.
Exactly.
And in the AI model, these weights are varied so that it has better and better predictions. And what's the consequence of having more parameters? How much of a difference is this resulting in the output or the apparent intelligence of the output?
What we figured out is that as we are growing these models, the performance just keep on getting better and better. So even the latest papers that had like 540 billion parameters was the latest model from Google called Calum. And then we had even trillions of parameters, but those are different types of transformers that are kind of sparse. Let's not get into those details for now. I think in 2020 appeared a paper from OpenAI called the scaling laws, and they showed that basically if you increase the compute, if you increase the number of parameters, and if you increase the number of tokens in your data set, we just keep on getting a lower and lower loss. Or equivalently, we get higher and higher performance on the downstream tasks of interest. That might be machine translation, so translating from a language to language. That might be question answering. That might be captioning. That might be open-ended dialogue. There are many tasks that you can put into that framework.
And does this have implications for imagery as well? And you mentioned at the beginning you're working on multimodal input, so not just text, but possible understanding of images or creating images.
100%. So the only thing you have to do is find a way to represent the image as a sequence of tokens. Once you have that, then transformers can handle it. And that's precisely what happened, I think, late 2020, when the Vision Transformer from Google again came out. And the idea is to take the image, basically patchify it or split it into these basically non-overlapping patches, and then embed those into some higher dimensional space. And then those are your input tokens that are the same format as with text, what I previously described. And so again, visual models now benefit also from scale.
And hence we get models like DALL-E and DALL-E 2 and Midjourney.
Precisely. Although those have a bit more to it. It's not just a transformer. There are these diffusion models. We might get into those a bit later if you want. And those are the latest and greatest so-called generative models. Before that, we had GANs or generative adversarial networks. Now we have diffusion models being the best class of models for that particular task of image generation.
I think we are getting quite close to the end of this episode. And Aleksa, you've done a really heroic job in explaining a number of concepts which I have been struggling with quite a while, and I'm sure lots of our audience have. I think if we could just round off with what GANs are, and then in the next episode, if we could come on to diffusion models, because they sound really exciting. So what are GANs?
GANs were invented back in 2014 by Ian Goodfellow. They are a class of generative models that work with images. And what I mean by generative is you're now not trying to input the image and output some class prediction. Instead, you're trying to generate the image. You're trying to model the underlying data distribution. Now, that might be a mouthful for your audience. Let me try and break that down. So how GANs work is you have two types of networks. You have so-called generators and you have so-called discriminators. And those two play or compete against each other, depending how you frame it, but people framed it as an adversarial approach. But you can claim it's also collaborative because, So what happens is discriminator basically tries to understand what's a real image and what's a fake image. So you feed it a real image and it outputs, for example, 1 or some number close to 1. And you feed it the fake image and ideally it will output something close to 0. And that's how it can discriminate. And then what the goal of the generator is to generate an image, and then once you pass that image to the discriminator, it needs to trick the discriminator into thinking that the image it just generated is real, i.e. we expect that the discriminator outputs 1. Again, same as for the real images. And in that type of a training, now there is obviously a lot of details there, you get a very high quality image generation from that generator model. And then you can just you don't care about the discriminator anymore once you're done with the training. And now you can just basically sample from that model and generate novel images. So you must have seen images. Some of them are kind of dedicated to maybe generative faces or animals or whatnot, but it can be much more general. And it can also be conditioned. You can tell it, hey, I want you to generate me an object of this particular class. Or even more powerfully, you can express that in human language. And that's where we get to the diffusion models and some of the latest and greatest image generation models, where you can specify via human text, via just a prompt, so-called prompt, you can generate arbitrary class, something very complex using human language.
So I believe that a number of years ago, Jan LeCun, one of the pioneers of deep learning, said that deep convolutional generative adversarial networks were the most exciting thing or impressive thing he had seen in deep learning for 10 years. But I guess you're going to tell me that there's even more exciting and important things happened in the last year or two.
Oh, 100%. This again is such an old architecture.
I think we should, at that point, announce a cliffhanger, because I think we're going to have to take that into the next episode. Like I said, this is a really terrific journey through the basics of transformers. David, if you're happy with this, I think we should wrap this episode up now and look forward to diffusions in the next episode.
Well, we'll just tell people that if they're interested in what's been said, they should check out your YouTube videos, and some of them may be less accessible, but some of them are more accessible, and they've also got some very nice graphics, more than just voices. And so that's on the website, which was called the AI Epiphany.
Yeah, and it's not a website. I only have a YouTube channel at the moment, and LinkedIn, Twitter, all of those stuff. But yeah.
Great. So let's take a pause now, and we'll come back in another episode shortly.
Thanks, Aleksa.
Thanks, guys.